Hello everyone, my name is Tuna and today I'm going to talk about ultra-low density digitally architected carbon with a 3D tube-in-tube structure. First of all, let me explain you what I'm going to cover throughout this presentation. I will make a brief introduction to structural architecture. I will talk about carbon aerogels. I will proceed to properties, application fields, and importance of carbon aerogels. And finally, I will end up my conversation with recent developments and architecture structures of carbon aerogels. First of all, what is structural architecture? Structural architecture is the study of finely and specifically designing the microstructures of materials in a manner such that the material has the enhanced and desired properties. These material properties can be thermal, mechanical, phononic, or physical. Throughout my project, properties of interest were mostly density and stiffness. In most cases, density is desired to be minimized to save cost, material, and effort. On the other hand, stiffness is desired to be maximized usually to avoid permanent deformations and fractures. As you can see from the figure here, density and Young's modulus has a proportional relationship. As density decreases, Young's modulus also decreases for most materials, which will in turn causes material stiffness to decrease. Therefore, it will be plausible to say that decrease in density results in rapid decrease in material stiffness. But there is a contradiction here, because I would like to decrease the density of the material, but I also would like to increase the stiffness of the material. Let me talk about properties of carbon aerogels. Carbon aerogels were used to be named the lightest material on Earth. They have exceptionally low densities, 0.0 grams per centimeter cube on average. They have extremely low thermal conductivities. They have high specific surface areas, which enables them to be surface active materials in chemical reactions. On the other hand, they also have some chemical properties. They are chemically stable due to the carbon atoms in the structure. They are environmentally compatible. They are modifiable and controllable. All these three makes carbon aerogels excellent catalytic and adsorptive. Let me talk about application fields of carbon aerogels. Carbon aerogels are widely used in energy storage areas such as supercapacitors. They are used as electrodes in supercapacitors. They are used as shock absorbers, rechargeable batteries. They are also used in separation of pollutants. Due to their high adsorptivities, they are used to separate harmful organic solvents, heavy metals, oils, and dyes. They are also used as nuclear waste storage. In the past 5 and 10 years, there have been a couple of developments in carbon aerogels fields. Heteroatom doping, compositing different materials, and structural tailoring are the methods used to enhance the properties of carbon aerogels. To begin with, heteroatom doping is replacement of carbon atoms by other atoms. These atoms are usually boron, sulfur, phosphorus, and nitrogen. By performing this process, the electronegativity, electrical charge, and electrical properties of the material change. It should be noted that whether the material is more or less electronegative than the carbon, the electronegativity of the material changes. Then, compositing with different materials of carbon aerogels this method is usually used to rapid capacity degradation in batteries by metal oxides, sulfides, and phosphides. The least but not least, 3D tube-in-tube structure enables the material have really high stiffness values and deformation recovery between 30 and 50% recovery proportions. This geometry can be defined as an inner tube connected by struts to another tube, and by integration of 3D printing into material science, this geometry can be produced easily. Due to higher connectivity and low transfer efficiency, this type of geometry has a stiffer material, and load is mainly distributed to outer tube and struts. Here are my references. Thank you for listening to me.